after.
Okay, thank you.
I just need to refresh my memory. We'll try our best to finish the assignment. So when is it due?
Due, I think not this week, next week.
Okay.
Friday? Oh wait, no, Thursday. 9th of May. Oh wait, no, 31st of May. So
Okay,
not this week, next week, Friday.
So when n equals to these numbers, you do prime factorization, list of divisors. For something like that, it was 1, 2, 2 squared, 2 cubed, right?
Yeah.
And that's why you get 4. 1 plus 2 plus 4, 7 plus 8, that's 15. That's how you do it. That's the sigma. And I think I wrote the conjecture for that.
I think we came up with one, but I'm not sure.
Yeah.
That's what the photo was of.
That's right. Let n equals to P1. Let me write it a bit bigger. So P1, K1, P2, K2, P3, K3, P, R, K, R, where Pn, I would say, where Pn is prime. So n is a number that represents all these numbers, okay?
Yeah.
Oh, actually, we shouldn't do n because it is n here. So we can maybe say where P1, P2, etc., all the way to PR are primes, different primes, okay?
Yeah.
And K1, K2, etc., KR are integers. But they don't have to be different integers, right?
No, they can be the same.
They can be the same. So I think that's fine. We don't have to say, here I said different primes, but here these are integers. So I'm not placing any or any integer. Or I would just say integers. So that's what you should say. Next, so that's just, we did a little bit of test for that. Then the conjecture is, so you don't have to prove it in this conjecture. The Dn equals to K1 plus 1, K2 plus 1, K3 plus 1, KR plus 1, okay?
Yeah.
There's a better way of doing this. You know what sigma is, right? Sigma
The
is
sum.
sum. So if you have like n, and n starts from 1 and ends with like 20, like 5, and that's equal to 1 plus 2 plus 3 plus 4 plus 5, right?
Yeah.
But if you have pi, like really big pi, with the n equals to 1 and n here with the 5 there, this means 1 times by 2 times by 3 times by 4 times by 5.
Okay.
So I can actually write this one as let n be pi with like R. So this ends with R.
Mm-hmm.
Starts with 1, and I can call this one maybe P. P starts from 1. So I just don't have any other variable. So P starts from 1, and P, little p, maybe I shouldn't use P, I should use Q. So Q here. And then this is a K of Q. So that's the same thing as this one here.
Okay, yeah.
Because you plug in 1, and you get P1, K1. Plug in 2, then you get P2, K2, right?
Okay.
You plug in R, PR, KR, right?
Yeah.
And then you can do this bit here where, so we can write where PQ is, I would say PQ, so Q is, maybe do the same thing where that, okay? Different primes, and K1, yeah, these are integers. Okay. So you can do the same here. And then you can say then.
Would it make sense because there's no like Q in the where P1, P2 thing?
Yeah, what makes sense?
Because the Q, how do you why does it suddenly change to 1, 2, and R? Like, do you have to state something?
Well, you're going to be plugging in 1, 2, 3, 4, 5, and up to R. So we're just saying that P1 to R, they're all different primes.
Okay.
And yeah, does that make sense to you?
Yeah.
Yeah, I don't want to do PQ because it introduces another complexity.
Okay.
So I could say that where PQ is, should we say different primes? But that's quite difficult because there is only a Q there.
Yeah.
If I say PQ is a prime, that means Q is not a specific number. So yeah, that introduces another difficulty. So I'm just going to put it like that, same as the above there. And the only thing that changes is you can write this one as pi, and then K, same thing. You start with the KQ plus 1, and then the Q starts from 1 and end with R, okay?
What's DN?
Oh, DN was?
Oh, is it the sigma n?
The number, DN was the number of divisors.
Number of.
Yeah.
Oh, yeah.
Yeah, so this is conjecture, just written in a different way here.
Yeah.
So whatever you prefer, you can use. So example, let's say n is, let's say, made up of 2 to the power of 2 and 3 to the power of 3, okay?
Yeah.
3 to the power of 3. Hold on. Maybe let's try 108. So let's have a look. Number of divisors of 108. So 108 has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So therefore, Dn is 12. Okay?
Yeah.
So the list is over here. So like this. So these are the divisors.
Oh, yeah, okay.
Now, but using this conjecture, first we write the prime factorization of this. So if we do 108 divided by 2, divided by 2. So it's 2 to the power of 2. And then 3 to the power of divided by 3, divided by 3, divided by 3, 3 times. So it's all just in terms of 2 and 3, right? So it's like that. So that's the... So obviously, this one here is 1, this is 2, this is 3, 2 square, 2 times by 3, 3 square, 2 square times by 3, etc., you know? Yeah, these are all the factors. Now, we can simply use, okay, so dn is given by 3 plus 1, right? This 2 here. And this 3 here.
Yeah.
Which is 3 times by 4.
And that's the answer.
And that is the answer. So it's working.
Yeah.
We can do another example, but we're going to move on. So this is the conjecture. So it says, based on the table above, basically, what was this one? This was 1 NP, right? So it was 2, right?
Yeah.
This was a 1N, PNP squared was 3. So this was 4. This was 5. This was 6, right? This was 1N, P and Q and P, Q. This was, so anyway, so you get all this.
Yeah.
So this would be 3 times by 2, which is 6 here. 2 times by 2, which is 4. 1, 2, 3, 4. 4 times by 2, which is 8. This one's n plus 1 times by 2. That's n plus 1 times by 2, because it's 1 plus 1. So that must be 2n plus 2, right?
Yeah.
So anyway, so these are all the answers, but the conjecture that can give all of the rule that encompasses all of this is this.
Yeah.
That's what it's saying. Let's move on to the next question.
Yeah, proving it.
Yeah, we have to prove it.
Yeah.
It's difficult.
Yeah.
We're going to do that next time.
Okay.
Now we're going to do the conjecture for sigma. We haven't found the rule for sigma.
No.
Okay, so sigma. So that was the sum of all the divisors.
Yeah.
Can you send me a picture of this?
Of which one?
Of this one here?
Oh, yeah, sure.
I just need to refresh my memory for it. So just on WhatsApp, take picture and then send it to me.
Yeah. Same.
Did you send it on still sending?
Yeah. Try to send again.
Okay, it has arrived.
Yeah.
I'm gonna download this. Open. I'm going to rotate.
Too much. Yeah.
So that one there is what we did. Okay, let's have a look. So we have, so these are all the factors. Yeah, that's right. And you add all the factors. That's right. Like this. So that's the rule for that one there. What about this? So it is definitely a difficult question. Question 7 is find conjecture for it. So I need a little bit of time for that. Emily, how many students are doing the double specialist?
5.
Second line. Only 5. How many students are doing?
6.
Sorry?
It used to be 6 last year.
Okay, who dropped out?
Lauren. I don't know. You don't know her.
Right. And how many are doing spec maths, the core, the first line maths?
A lot. I think maybe almost 20.
20. What about physics?
Maybe 15.
15 only.
Around there. Yeah.
I heard that in year 11 there's a lot.
Yeah, I think there's a lot more in year 11.
And they drop it in year 12.
Oh, there wasn't, I think, yeah, quite a few people dropped, but also because we used to be combined with the IB, but now we're not.
Right.
Yeah, so they're all
separate. Right. So when you say 15, it's not counting the IB?
No.
Okay. Okay, so we need to come up with that's when you have the P only. When you have Q there,
yeah,
it gets a lot more complicated. Let me just give me a second. I'll just try to figure it out. Okay. We figured out the rule for dn, true?
Yeah.
So that's k1 plus 1 times by k2 plus 2. Now plus 1. K3 plus 1. So we have to actually use this one, I think. Say you have, so basically these are all factors, right?
Yeah.
And the number of all of that,
like added together,
all of that is 4, and that's the dn.
Yes.
So how does that work in this case? Conjecture. So based on the table above, and you answered to question 5 and 6, that's right. State a conjecture that relates this one to n's prime power decomposition. Be clear to define any variable. So
does it have anything to do with like Fermat's theorem thing? Fermat? I don't know. I literally have no idea.
Not so sure about Fermat. Let n be the same thing as this one here. And dn equals to this. This is the number of the primes. This is way more complicated.
Yeah.
Conjecture. This is the conjecture for just that one only. Now, if you look at this one here, this is made up of that bit there.
Yeah.
And that bit there.
Yeah.
So obviously for sigma P and Q is Pn plus 1 minus 1 over P minus 1. That's the blue bit. Plus, if we factorize Q out of it, then that's just equal to 1 plus P plus P squared plus what? Pn. So that's the yellow bit, isn't it?
Mm.
So same happens here as well. You got this one.
Yeah.
And you've got this one here. But if you factorize the Q, then 1 plus P squared, which is same as this one. So this is equal to Pn plus 1 minus 1 over P minus 1 plus Q bracket Pn plus 1 minus 1 over P minus 1, right?
Mm-hmm.
So that's the rule for the second one there. Let's go for PQ. Let's suppose that we have P1, P2.
Can we use the same start as the other one before? Like
same start.
Like the let n equal the pi thing.
Here.
Yeah.
Yeah, so I'm getting to there. So we're going to do P and Q N1, N2, okay?
Okay.
Then I think this will look like this. Sigma of that is going to be this one here.
Mm-hmm.
First of all, P N1 plus 1 minus 1 over P minus 1. And then you'll have Q. If we just had one Q, you just end up with Q there, and then you have you ended up with exactly the same thing as this one, right?
Yeah.
That was the answer before. But I think if it's N2 there, it will be Q squared with exactly the same thing here. Let me actually, and this will be extremely difficult to prove. If I have P in there and then Q squared instead of Q, okay, then I'll probably end up with this, this, and this, okay?
Mm-hmm.
Which is equal to, because it's the same stuff. It's like that, and then 1 plus Q squared, right?
Yeah.
Which is that stuff there, again, with, first term is 1, so it is a Q to the power of R, which is 2 plus 1, which is 3. AR, R to the power of N is, there are 3 terms, minus 1 over this. Okay. So perhaps if I have sigma P N Q3, then it'll be just let's say P N1 Q N2, then it'll probably be, conjecture is, this one here. In this case, I'm just going to get rid of the N there, N1, N1. it will probably be this one with Qn2 plus 1 minus 1 over Q minus 1.
Mm-hmm.
So that's my conjecture for P and Q and 1 and 2. So I'm going to have this really bold conjecture. Let's say you have P1. Let's say we write so this is some practice. So here goes my conjecture. Same as this one here, almost the same.
Yeah.
Do that first. Then sigma of n
Mm-hmm.
is going to equal to P1, K1 plus 1 minus 1 over P minus 1, not P1 minus 1, P2, K2 plus 1 minus 1, P2 minus 1, all the way up to, we times it, keep timesing it, PR, KR plus 1 minus 1 over PR minus 1.
Mm-hmm.
So let's just test it, okay?
Yeah.
So I'm going to use, we used 108 before, right?
Yeah.
So maybe we're going to use 2,700.
Mm-hmm.
2,700. And divisors of 2,700. Well, there are a lot, you know?
Yeah.
Oh, there is some rule here.
Uh-huh.
They're giving some formula.
P.
Oh, that's another way of writing the prime number, right? I mean, prime factorization. 2,700. List of divisors.
Well, that's a lot.
There you go. Number of divisors. Some is this one, right?
Yeah.
So Google is the best. So this is our test. So we're going to see if this is working, okay?
Okay.
So that is 2,700. And this is equal to 2 to the power of 2 times by 3 to the power of 3 times by 5 to the power of 2, I think. Because 2 squared, 3 cubed, and then 5 squared. Times. Yeah, 2,700. Yeah. So we obviously know that dn, we can test our dn. That's 3 times 4 times 3, isn't it? That's 36. That's true.
Mm-hmm.
So because of 2, you get 3. Because of 3, you get 4. Because of 2 here, you get 3. Now, sigma n is That's the answer there.
Mm-hmm.
We want to do 3. No, 2. 2 is the prime.
Yeah.
2 to the power of 3. Because it's 2 plus 1, right?
Yeah.
3 minus 1. 2 minus 1. 3 to the power of 4. This number here.
Yeah.
Minus 1
Over 2.
over 2. I'm going to write it as 3 minus 1. And then this is a 5 to the power of
3 minus
3 minus 1.
From 4.
So that'll be 8 minus 1, which is 7 over 1. That's 81, 80, that's 40. And that's 124, 124. That's a 31. If you times it, what do you get? Oh, it's
Yay.
working. Yeah, we got it.
Okay.
So it is working.
Yep.
Yeah. But to prove it, that's gonna be even more painful than the other one. Yeah. But we'll do it, okay?
Mm-hmm.
We'll get there, don't worry. Got plenty of time, so. We only had one lesson on it, right?
Yeah.
So this is our second lesson, so probably this assignment is like for 3 hours. 3 hours of tuition. So that's the conjecture.
Yeah.
And I think it's correct. Now, going back to the assignment. Next part is prove the conjecture. Did we do this part?
No.
We didn't?
So I think for that part you have to use the stuff from.
Yeah.
Oh, I think we did A.
We did A.
Yeah.
Well, I think you can do D and sigma for this one yourself, right?
Mm-hmm.
That's pretty simple. All you have to do is just do prime factorization and use the conjecture.
Yeah, now that.
And the answers for this is available from Google. I think we went through that, right?
Yeah, I think we did.
Yes. Can you show me the photo of this? Did I write it somewhere? Do you have that with you?
For B. I don't think yeah, I have it. I don't think we actually did B. But I think that one, now that I know the rule.
Okay, so I'll leave that to you.
Yeah.
Then, so what is the smallest integer n? So we didn't do this one, right?
No.
Support your answer. Yes, C and D. Okay. That goes there. And the conjecture was this one. That's the conjecture. Okay. So the dn must be 8. So all I'm saying here is that these k's are, of course, integers. And these k's, it can't be 0. It has to be at least 1, right?
Mm.
The reason why it's at least 1 is because if it's 0, that means you don't have prime factorization in terms of like P1, for example. Yeah, so they can equal to 0, but that means you just don't have the prime.
Yeah.
Certain prime is just not there. So, rigorously speaking, k's are at least 1s for the primes that factorize the n, and the k's are 0s. They're 0 for primes that doesn't factorize the n. Okay. So I should say here, we can actually edit this one and say positive integers. We have to actually change this to positive. So make sure you put this one into all your solution, okay?
Okay.
So the k's are integer exponents and they are at least 1, so they cannot be 0. Now, we need to figure out a way to get 8, okay?
Okay.
So one way is obviously, so possibility 1, you can have 7 plus 1.
Yeah, and then would it be like
right?
3 plus 1 times 1?
You cannot have 6 plus 1
No.
times by something is not 8, right?
Yeah, it's not. So maybe 3 plus 1 and then 1 plus 1.
3 plus 1, 1
Mm.
plus 1.
Yes.
So that one there, that one there, that one there, right?
Yes.
Is there any other case?
You can do the 1 plus 1 times 1 plus
1
plus 1.
Plus 1,
And then 1 plus
1 plus 1, 1 plus 1, 1 plus 1.
Wait, no, only 3 of them, right?
Only 3 of them, that's right. So in that case, that gives you 8 as well.
Yeah.
This one is 4 times by 2, which is 8.
Yeah.
So we have to start with 1 and 1 and 1. All of them is 1. All of them are 1. And then what about 2? Start with 2. Can't, right? Because as soon as you do 2, then plus 3. And 2 times by no integer. Yeah.
Yeah.
And then you have 3. So that must be odd. What about 5?
No, because then it's 6.
That's right. Then you can't get integer, right? So these are all the cases.
Yeah.
And of course, you have to make some argument here. Argument on why these are the only cases.
Can you just list all the factors and like?
Yeah, maybe you can do 2 and show that it doesn't work, and go for 3 that show it works with a 3 and 1. Now, case number 1. So that means there's only one prime, right?
Yeah.
1 prime.
You always use the smallest prime, not like 2, because it's the smallest.
Yeah. So obviously let P1 equals to 2. Then you have 2 to the power of 7.
Yeah.
That'll equal to how much? 2 to the power of 5, 32, 60, 64, 128. Right? Yep.
Mm-hmm.
And then you go for the next one.
That's 2 to the 3
P to the
times.
power of 1 to the power of 3. P to the power of 1, right?
Yeah.
So just make it equal to 2 to the power of 3 times 2 to the power of 1, right?
Yeah.
We'll go for the smallest one. So.
Wait, but then didn't they have to be different primes?
Oh, they have to be different. That's right. Very good.
So
Very
should I
good.
get rid of that? Because does it still work if it's the same prime? Like the
No,
rule?
no, no. I think it'll have to be different prime. Otherwise, because we define, you see, over here.
No, but like,
they're all different primes.
wait, should we try that one by using like 2 different primes and see if it still works?
2 different primes.
Like, yeah. Like, would it still work if you used, just say you did like 2 squared times 2, and that is just 8, but would it still work? Like the rule?
I'm not really sure what you're talking about. Hold on.
Like if you use, so with the conjecture, if I changed it so it's the same prime, would it still work? Like it could be the same prime. Would it work still?
Are we talking about something else or this one here?
Well, like relating to it.
Relating to it.
Like does it actually have to be the same prime?
No, they have to be all different primes.
Does it have to be?
Yeah. So I don't think it'll work if you use, let's say, well, it's a bit of a contradiction because as soon as you do 2 to the power of 2 and then 2 to the power of 3, these are 2 same primes there, right?
Yeah.
Let's say this is at 1 there. So this is actually the same thing as 2 to the power of 5 times by 3, true? Now, the dn for this one is going to be 5 plus 1 times by, this is 1 here, so it's 1 plus 1, which is equal to?
2.
6 times by 2, which is 12, right?
Oh, sorry, 12. And then the other one's
what
different.
What about this one? D of n is going to be?
3 times 4 times.
3 times 4 times 2, which is...
that's bigger.
That's 24.
Okay,
So it's never going to work if they're the same primes, okay?
Yeah.
Yeah. Do you know the reason why it doesn't work?
Sort of-ish.
So the reason is we derive this formula by assuming that they are all different primes.
Yeah.
Yeah. And it's a little bit complicated. So if they're actually the same prime, then everything breaks down. This formula doesn't work.
Okay.
So anyway, so if you got 3 there, 1 there, so you have two possibilities, right? This or 3 to the power of 3. But you pick the smallest prime, 2 primes, right? Smallest 2 different primes. So you get that, which is 8 times by 3, which is 24.
Yeah. Or 9 times. 27 times.
54.
Yeah.
Yeah, 27 times by 2. So that's case number 2. And then the next one is P1 to the power of 1, P to the power of 1, P3 to the power of 1. So you just go for, because we want the smallest, so we just ignore that. Okay?
So 2 times 3 times
2
5.
times 3 times 5, which is 30. So the answer is 24.
24.
So do you think you can make some argument for that?
Yeah.
pretty straightforward, I think. So do they all have DN8?
I think so.
Yeah, factors of 128. 1, 2, 3, 4, 5, 6, 7, 8. That's right. 24. One, 2, 3, 4, 5, 6, 7, 8. 30.
And 54.
Yeah, 1, 2, 3, 4, 5, 6, 7, 8. So if you're not doing it this way, then you have to actually start from 1 and end with 24 and do every single one of them and figure out the DN for it. Do you know what I'm saying? Yeah, but this way is a bit more, yeah, so it's not, 24 is such a small number, so you can actually just do it by trial and error, do it for like 20 and 21, 22, 23, 24. None of them will have, the first time the DN appears to be 8, appears as 8 is when it's 24.
Yeah. Okay.
So yeah, there are two ways of doing it, either by trial and error, or what we just did here. Or either way, you can support your answer, right? But probably your teacher wants you to do it this way here. In 1644, Mersenne asked for a number with 60 divisors.
So DN equals 60.
Find one smaller than 10,000, clearly showing how you found it. Number with 60 divisors. Okay, less than this one.
Yep.
Well, this is a lot more complicated.
Yeah, it's bigger.
So this one is so we're going to do prime factorization of this. Because k is also integer. So if we do 60 divided by 2, so it's 2 squared. So 60 is 2 squared divided by 3 divided by 5. So it's times by 3 times by 5. So definitely this must be 2 plus 1. Hold on. This is made up of k1 plus 1. So k1, k2, they could be the same, you know?
Yeah.
Let's actually find all the factors of 60.
It's like 1, 2.
Yeah, factors of 60.
There's not that many.
There. These are the factors of 60.
Yeah.
And we have to figure out number of ways we can form this one. So we cannot use, can it be 59? You cannot have 0 for this one, right?
No.
So we have a few possibilities. Hold on. Let's say we use 2, okay?
Yeah.
Well, there's just so many of this.
Yeah, there really is. Maybe there's another way.
You can do like 2 times by 30.
There's a lot.
Then it's equal to 1 plus 1 times by 29.
Then there's so many different things.
Yeah, and then you can do 2 times by 5 times by 3.
Yeah. That,
And
and then times 2. So 2 squared times 5 times 3.
Yeah. There's just crazy many possibilities, right? I don't know how to do this one at the moment. So we'll leave it there. Yeah, this is a crazy one. Just giving up for now. How did we do this one here, though? So this was 8 here.
That's because there weren't that many things. But then this one has a lot of things.
If you have factors, then... So these are the factors. As you go down to lower numbers, it gets more complicated, right? That's the only way for that. What about with 15?
4. 2 squared.
4 or?
15 times 2 times 2.
In that case, it'll be 14, 1, and 1, right?
Yeah.
So these are the only ways for 15, right?
Yeah. Or 5 times, they can do 5 times 3.
Yeah, well, but I'm just going to be doing 15. Starting from here. I have to use this one. 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 So that's how I'm going down. Okay. So I'm not breaking this down into
Okay.
5 times by 3 because that's over here, you know?
Yeah.
So what about with 12?
12.
I have to use this one.
5.
So again, 12 times by 5. Is that the only one?
That's all.
Yeah, because this cannot be broken down any further, sure?
Yeah.
And let's suppose I have to use
10 times 6. Or 10 times 2 times
So
3.
this can be broken down into 2 and 3?
Yeah.
That's the only possibility, right?
Yeah.
So with these numbers, it's quite simple. But now it gets complicated. If I have to use 6, well, then it's 10.
Oh, we've already done that, so you can cross that out.
Yeah, or 6 times
6
what?
times 2 times 5.
2 times 5.
Yes.
So that's already there, right?
Yeah. Okay, then 5.
And then if I have to use 5,
Yeah. 5.
then I have to use 12. Well, that's already done here.
Yeah. So 5 times 3 times 4. Or 5 times 2 times 6. Or 5 times 3 times 2 times 2. Or 5 times
5 times.
2 times... Oh, wait, no, that's it, I think. Yeah, that's it.
If I do 5 times 3 times 4.
So that's 5 times 2 times 2.
It's a matter of how you break this down, right?
Yeah.
You can break it down. This is a 2 square times by 3.
Yeah. Or 4 times 3.
So
Or
you can make 12 like that.
Yeah.
So it's a 2, 2, 3. So you can do 4 times 3, 6
Yeah.
times by 2. So, or all individually. So you have to group it like that, like this. Group it like that and this. 2 and 3, or 2 with 2. Yeah, and the 2 and 2 and 3 separately, right?
Mm-hmm.
That's that, like that, okay?
Yeah.
Okay, now, so we crossed that out, but this was, oh, it's already here, this one, 625.
Yeah.
So cross that out. This is not there. That's not there, right?
Nope.
Let's now move on to, I've
4.
got to use 4.
So 4 times 15, which
4
is
times
18.
15. Is it there? It's there,
Yeah.
right?
Mm-hmm.
Or I need to break down the 15 into
3 and 5.
3 and 5. So this is a
Yeah.
pretty simple one.
Yeah. Okay.
So it's
So
4 times by,
3 times 5.
which is already there, no?
Yeah.
So both of them. So that's the only way, right? Yeah.
Yeah. And that's already there as well.
That's already there.
Cool.
And then down to, I've got to use 3.
3.
I must use 3.
3 times 20.
So 20 is broken down into 2, 2, 5, right?
Yeah.
So there's a few ways of grouping them like this, like that,
Or individually.
or individually.
Okay.
So this gives us
3 times 4 times 5. Or
3
3
times 2
2
times
times
10,
10.
3 times 2 times 2 times 5.
Yep.
So this is already there,
Mm-hmm. I think,
and that's already there as well.
yeah.
There.
So is that one.
So is this one.
And so is that one as well.
So is that one there as well.
Yeah.
Is it 3 times? Yeah, 10 times. Yeah,
Yeah.
that's right.
So
Okay.
now 2.
2 times by
30.
30. 30 is?
3, 5, 2.
Well, that's the only way, right?
Yeah.
So all individually, right?
Yeah.
Is it there?
Yes.
It is, right?
And the
Same
other
thing.
one.
This one's there as well.
3 times 15 times 2.
3 times, oh, 15, that's
So
right.
2 times
So we can group it like this.
2 times
Group
15
it like that.
times
Group
2.
it like that, right?
Yes.
So that's individually. And 2 times by 6 times by 5.
Yeah.
2 times by 3 times by 10. 2 times by 15 times by 2, right?
Yes.
Okay. So was this one there? 2, 2, 3,
Yes,
5, right?
that was that. Mm-hmm.
2, 6, 5. 2, 6, 5.
Mm-hmm.
It's there as well.
2, 3, 10 also, yes.
2, 3, 10 also there.
And
What
so
about
is that one.
2, 2, 15?
Yeah.
When we did 15, it's already there.
Yeah.
So
And so is
yeah.
the first one. Okay, that wasn't too bad. Okay.
So
Not
maybe
that
maybe
many.
make a table for all of this, and then
Yeah.
let's cross them out and give explanation. So what we have is just those, right?
Yeah.
Mm-hmm. Let's write it down here again. So 1 by 60. 2. But that's impossible. 1 is not possible. That means k must be 0.
Yeah.
So I'm going to cross that out with the different color.
No, but then you just do the 60. So like 59 plus 1.
Yeah, you can do 59 plus 1.
Yeah, so just that. So then 2 to the power of 59.
Oh, just by 60 itself.
Yeah.
Yeah, that works. Yeah.
So you just do 60 without the times 1. Yeah.
Okay. You're very good assistants. All right. 60 for 30. I'm going to do 2 times by 30. 3 times by 20. 4 times by 15. And the 5 times by 12. And then 6 times by 10. And then that belongs there because it's involving 6 there. So I'm going to write it here, 6 times by 2 times by 5. 10 times 2, so that's 2, 3, 10. 2 times 2 times 15. 2 times by 3 times by 10. So I did that, right?
Oh, I know you haven't done that.
Oh.
Wait. No, you haven't done the 10
10
times 2 times 3.
Yeah. Here.
Or did I just...
1, 2, 3, 4, 5, 6, 7.
Oh, okay, wait.
9.
My thing was covering it. Never mind.
1, 2, 3, 4, 5, 6,
I just lost
7,
it because my
8,
thing was
9,
covering.
right?
Yep.
Yeah.
And then, so 5 times 3 times 4.
5 times 2 times 2 times 3.
Yep. And 5 times 3 times 4.
Yeah, 5 times 3 times 4. Let's actually rearrange them. Hold on. Actually, I'm going to erase this. I want to write down the lower number first.
Yeah. So 2.
So that's 2 by 30, okay? And then 2 by, so anything that involves 2, okay? So there's 2 there, 2 there, 2 there, 2 there, 2 there, right? Okay, so I think the answer is most likely 2, 2, 3, 5, this one here.
Yeah.
So 2, 2, 3, 5. And then 2, 3, 10. And then 2, 5, 6. And then 2, 2, 15. And then 2, 30, okay?
Yeah.
1, 2, 3, 4, 5, okay. I'm going to now do the ones that have 3 as the smallest. Is that right? 3, 4, 5, 3, 20. And then I'll do the 4, 15. And then 5, 12, right?
Yeah.
And then 6, 10. That's all done. And then finally it is 60. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
Cool.
So these are the ones that give you K1s and K2s, etc. So this is equivalent to power of 3, power of 3, power of 4, power of 5. And you can
Wait,
have
isn't it the opposite? Power of 1. Wait.
Power of 3, power of 3. Oh, that's right. Power of 1, sorry. Yeah, sorry, I'm a bit tired. Power of 1, power of 1, power of 2, power of 4.
Yeah.
And you have a bunch of prime numbers go there. And yeah, so on and so forth, you know. This, power of 1, power of 2, power of 9. And of course you can do like 2, 3, 4, 5, but I would rather do 2 here, you know? So
yeah.
The algorithm is you put 2
The highest.
for the highest
thing.
Yeah, highest power. And then 3 here, 4 here, 5 here. So that's the algorithm.
5 and then 7.
Yeah,
Primes.
that's right. And here 2, 3, 4. Easy?
Wait, it doesn't have to be prime numbers. So
oh, yeah, that's right. Oh, yeah, sorry. 2, 3. What am I doing? 2, 3, 5, 7.
Yeah.
Yeah, you're very good assistants today. Thank you so much. 2, and then 3, and then 5.
Yeah.
That way you can ensure that you get the lowest number. Okay? And this as well, you go 5 here, 4 here. Yeah, so these are the K plus 1, that's right. So it has to be one value lower, right?
Yeah.
Yeah, so 2 here, 3 here, 5 here. So you do it for every single one of them.
And then find the smallest.
Has to be the one that's less than 10,000.
So as soon as you get
smaller than 10,000.
Okay, so as soon as I get to one that's less than 10,000, I can just say, there we
go. It's not saying the smallest, so it's actually quite easy. You don't have to do. You don't have to do all of this.
I'll probably just end up at the 2 times 2 times 3 times 5.
Yeah, so this is 2 that I think that will give you. If we just look at that, 16 times by 9 times by 5 times by 7. That's 5,040.
Oh, that's already so much smaller.
Yeah.
Okay.
So let's have a look. 5,040. Number of divisors.
That looks like 60 to me.
Does it look like 60?
Yep. Not going to count.
Number of divisors. Yeah, 60 divisors.
Yep.
So it is working. I think we should call it a day here.
Okay.
We can go through the proof and the last question, I guess. So we pretty much, pretty much finished this one here. What is this thing about? I'll print it out and do it by myself.
Part B as well.
Yeah, I'll have a think about this by myself. Okay, cool. See you next time.
Okay.